Now I want to introduce so-called quasi-particles and excitations. But first, let me introduce some symmetry. So in condensed matter, we don't have Lorentz invariance. Lorentz invariance is completely irrelevant for any condensed matter system, and it only makes things harder for you. So nobody does that. Rather than that, we have so-called Galilean invariance. So the picture is something like this. We have some fluid. So this is fluid, and there is, if you want fluid at rest, and there's like some observer O moving with velocity v. And the relationship between these two reference frame is like, let me put prime for observer, r prime is going to be equal to r minus v of t, right? So this is the Galilean invariance, and that's all you need. There's no other, right? In the Lorentz case, you also need to do full Lorentz boost, but here that's all we need. You want momentum in the prime frame is going to be momentum minus mass times v. So this is correct transformation for each particle with mass m in fluid. Good. But now I also want to understand how energy transforms, right? So this is the momentum, this is the position. Like, so right now we are doing classical physics. In a little bit, we are also going to think about quantum physics. So we have energy is equal to p squared over 2m. And this one is going to go to E prime, which is going to be P minus mv squared divided by 2m. And if you open this up, what you are going to find is P squared over 2m minus P dot v plus 1/2 mv squared. Right? So P squared over 2m is E. If you want, there's like E of P minus P dot v. So this is just a constant shift. So it is, you want kinetic energy of the frame, it's not relevant, but this is the p-dependent piece of shift in particle energy. So then E of P prime, if you want, E of P is going to go to E of P minus P dot V. So with the Galilean transformation, and P is going to go to P minus mv, and V is the frame velocity. Good? Any questions? So trivial stuff. Now let's think about quantum mechanics. So in quantum, P is derivative of x, right? We don't have like a new variable, and velocity is, if you want, we are thinking about expectation values, and then when we define velocity, we take the time derivative of expectation values. But anyways, let me write it in one dimension and then write what I mean. So in one frame we have x prime, and the other frame I have vt. Suppose I just think about a one-dimensional case to simplify the notation. Then del x prime is equal to what? from here. So this is the only transformation I said we need. Now I want to also write the derivatives in the primed frame. Right? This is like a simple thing. What is the relationship between del x prime and del x?
This part of them might maybe the time derivative.
But there is no time. This is already partial derivative, right? This is already partial derivative. There is no time. So del x prime is equal to del x. Right? Simple. Now, if we write the Hamiltonian h lab, right? I need to write minus h bar squared over 2m del squared del xi squared. But I need to write this for each particle xi. So this is the kinetic energy of each particle, and I also have V of interaction between the particles. So the way I write this is like I less than j, 1/2 V of xi minus xj. And the other one, h, let me call it h moving Hamiltonian, right? So because every coordinate is shifted the same way, interaction first is trivial, it's not going to change, right? I'll put like a shift here, I'll put a shift here, they'll cancel each other. Interaction, if you want two particles, whether you move or like you are at rest, doesn't matter. The distance between them matters, so they don't change. And from this relation, we also have h bar squared over, if you want, I will put prime here, it doesn't matter. So this is I del squared del xi primed squared. So basically, whether you are moving or at rest, Hamiltonian is the same. It doesn't change. So we said, so h moving is equal to h lab. So Hamiltonian is Galilean invariant. However, wave function is not, right? Let's write wave function for lab. Let me use psi 0, and to shorten the notation, let me use this bracket notation. Suppose this is defined as the wave function I wrote above. This is psi of r1 dot 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 rn. Think about like a plane wave, right? And then now, so this is lab frame. I want to write another wave function which is moving with respect to lab frame. How does it change with respect to this one? What should I do to go from this? I take like a blob, right? This is blob of wave function. And if I am at rest, it is like this blob. But if I am moving, suppose I'm moving, I don't know, this way, then from my frame, this blob is going to be moving like in the opposite direction. But to have this effect in the wave function, how do we put this in quantum mechanics? Yes, phase, right? And the phase is going to be e to the I. If let me just write q, and let's try to find q in terms of frame velocity. Q dot, and I have to put phase in each for each particle. So this is going to be r1 plus r2 plus dot 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 rn, and this is going to be psi 0. Good. And if you want, this is kind of like a unitary transformation. And the nice thing about this phase is it also obeys Bose symmetry. Now what I want to do is I want to calculate momentum and Hamiltonian with both of these wave functions. I want to calculate the expectation value of momentum and Hamiltonian with this, and expectation value of this, and it's going to tell us how energy and momentum changes in quantum mechanics. So let me define total P is going to be I is equal to 1 to n Pi, and Pi for each particle is minus I h bar gradient if you want, or to make it simple, let's write one dimensional, right? It is easier to write in 1D, so this is, and then generalize it to any dimension, Pi. So lab frame, so this is total momentum, like all particles summed over, so this is P. Let me write 0 for the lab frame, and this is going to be what? So 0, right? Because there is nothing moving, so it's like stationary blob. So this is 0. And I can also calculate Hamiltonian with this, and let me define this to be E naught. So this is the ground state. Now, moving frame. Again, exactly the same operator, because operators do not change, but the wave function changes. So that's why I'm going to put like a m here. What is this thing? Based on this wave function. Every time you act on here, it's going to bring down a Q factor, and it's going to bring down Q factor for each particle, right? So this is going to be h bar Q, and you are going to have n of these. Oh, I forgot to mention here. Q, I choose Q's such that h bar Q is momentum is going to be m times v, and this is frame velocity, and I want to write it here, h bar over m times v. And now Hamiltonian h in m is going to be psi 0 e to the minus I q dot r. Let's define r to be r1 plus r2 dot 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 rn. I have h, and I have e to the I q dot r psi 0. And if you do all of these things, right, this is like, there is like an interaction term, it commutes with this, it has nothing to do with this, it's going to go this way, and interaction term is going to be unchanged, but there are going to be derivatives, and derivative is going to act on here or here, and you open up and you do the cancellations. At the end, what you are going to find, okay, this is like if you want exercise, if you have the appetite, you can spend like 2 minutes to do this. What you are going to find is this is E0 plus h bar squared q squared over 2m times n. And you can see there is no linear term. Try to see that for yourself. And this thing, if we use this PM, this thing can be written as E0 plus PM squared. So there's like n squared, h bar squared, q squared. And I need to divide it by another n to get the same thing. But rather than doing that, I am going to define something like this. And m is going to be n times m. Now, this equation, so this equation and this equation is going to define Hamilton's equations, right? Let me put 2 stars here. And what it tells us, this and this are exactly Hamilton's equations of motion for a particle which, for a fluid which moves with momentum p m and total mass is m. And yeah, this is kind of like a silly exercise, but what this proved us is like the whole fluid moves, not just superfluid portion. So as a result, here's the upshot. The condensate and 0 is equal to 0.1% of total density, or condensate particles is 10% of all particles. So this is condensate. But superfluid density is equal to total number of particles. And this is a consequence of Galilean invariance. And from here, that expression we found, like the superfluid density was found to be like ns times v of s. And here this ns is equal to total density. So this is going to be n, and vs is going to be h bar over m gradient of theta. And let me just write that and finish. Superfluid. So we introduced two things like condensate density and superfluid density. And superfluid density is same as total density. Good. Maybe any questions? So let's talk about superfluidity and Landau criterion. So superflow was observed by Kapitsa in 1930s. And I think Kapitsa got his Nobel Prize something like 40 years later. And I think so I don't remember the other people's names, but there were like 3 people. Kapitsa was given Nobel Prize for his work on superfluid, but other people were working on I think cosmic microwave background radiation, something like that. They have nothing to do with each other. I think something like that happened in a couple of years ago. But the results is something like that. So the confusion was like different experiments gave different results, and there was so-called two-fluid model. Two-fluid model. Now I introduce all the ingredients. We know there's like a superfluid and the normal fluid, and there's like normal plus and super. So this is normal. So this is super. And the behavior is something like this. So as you go to lower and lower temperatures, so this is T. So this is, for example, N super. There's like a critical temperature. And you go 0, 0, 0, and then it shoots up. And at T is equal to 0, Ns is equal to N. And similarly, normal component, it's like 1, 1, 1. As soon as you hit the critical temperature, it starts decreasing exponentially. And this Ns, for example, Ns is known to be some constant times Tc minus T to the nu for T less than Tc, and 0 T bigger than or equal to Tc. And at low temperatures, Ns of T is something like some N minus some constant A times e to the T4. And this nu, again, is 0.67, which is exact match with XY model. I don't know, we may or may not talk about XY model, but let's keep that in mind. And the the observation of superfluidity is something like this. You put like a thin pipe, right? This is, if you want, these are walls of the pipe. So this is walls, and there's like a fluid. Normally, if you have like a water, normal fluid, as it moves because of viscosity, it slows down, right? If there's like a velocity here, v, as it moves, it's going to slow down and it's going to dissipate energy, and there'll be heat and all those things. But in the superfluid, there's no such thing. So it just keeps moving without any slowing down. So no viscosity and no dissipation. Dissipation. And the question is, why is this happening, right? Why is there like a superfluidity? There's like a normal component and superfluid component. It's like a complicated system. Even though superfluid density we have shown to be equal to total density, we still need to explain a mechanism for this behavior. And this came from Landau. Okay, maybe the reference I use is not on it. Here I use reference Landau and Lifshitz, Statistical Mechanics, Volume 2. And Atlant and Simons also has the same argument. It's like a one-page argument. And let me remind you the Galilean transformation, because I'm going to use it. So first, Galilean transformation. So there are like two reference frames. One is, if you want, at rest, and the other one is moving with velocity v. And what we found here is, like, if you have momentum p and energy of EP here, the transform variables p prime is going to be equal to p minus mv, and E of p prime is going to be equal to E of p minus p dot v plus 1/2 m v squared. Again, this is a constant piece, that doesn't matter, but this minus p dot v is kind of like a Doppler shift, right? Because energy, if you think about in quantum sense, is kind of like a frequency, and if you have like a shift in that frequency, that proportional to the wave vector and the observer speed, you have like a Doppler effect. And now we want to understand why there is no viscosity. So the question is, why no dissipation? And it's easier to start from the okay, the original problem is, again, this, let me copy this. So this is the original problem. But this is not easy to, as easy to understand. So Landau suggested that let's not think about this. Let's go to a frame where the fluid is at rest, right? So this is fluid at rest, but the walls are moving. So the walls, like, in the opposite direction, if you want. And what happened is, like, I don't know, the wall, I draw it like a smooth surface, but maybe there's like a bump here. Microscopically, if you go there, and there are like helium atoms, and as you like pass the wall through the helium atoms, maybe like there'll be like helium atom colliding with the bump on the wall and changing its energy, right? And that's the mechanism of dissipation as we understand it. So this is so there's like some after like colliding with the wall, it increases its energy, and this thing we call it an excitation. Because if it doesn't increase its energy, it's in the ground state, and there's like a superfluid, and there's nothing to talk about. And this excitation is going to have like some energy, E of P, and again, let me write P too. There's like E of P, energy of excitation, and there's like a corresponding momentum, and this is momentum of excitation. For like a classical fluid, this E of P is what we understand, right? This is P squared over 2m. Even in like more complicated cases, we can approximate it like P squared over m star with effective mass. But in the generic many-body system, we don't know what it is. It could be a very complicated object, right? Because it has to know about interaction, right? You have to solve full many-body problem and then arrive at the energy. So this is complex many-body object. So let's keep it general. Now, so this is the frame where the fluid is at rest. And Landau suggested let's now go back to lab frame, because we see the superfluidity in the lab. Now, go back to lab frame. And we have already like a prescription for going to lab frame. If you have P and EP, going to lab frame means just shifting momentum and energy exactly like this. You just go back. And if you go back, what you are going to find is lab frame, fluid moves in the lab frame. And what you are going to find is this usual E of P. And we, in the top, we had like this minus V dot P, right? But this is in the opposite direction. The sign doesn't matter, but let me just be careful about that. And plus this 1/2 m V squared. And this is the frame velocity. So again, so this is the frame kinetic energy. It doesn't depend on P, so we don't care about this. But this one is energy due to excitation. Now, let me just emphasize that in a many-body system, you cannot just go and put particles at any energy as you wish, right? We know this from quantum mechanics. There's like very strict energy constraints. For example, if you are a particle in a box, there are like discrete energies, or if you are in a superconductor, we'll come to that, there's like a gap. And in helium, there's like a many-body system that has like a well-known spectrum that I'm going to tell you in a little bit. But energy spectrum determines what happens. So the excitation has to obey that. And the Landau's argument is like this excitation, for it to happen, right, after bumping on the wall, it has to be favorable. If it's not energetically favorable, it will not happen. Also, we are thinking about at t is equal to 0. And this happens when E of P plus V dot P is less than 0, right? If there's like an energy cost at t is equal to 0, you cannot make such an excitation. And to understand this, we can just consider the minimum value of this. If the minimum value of this thing is less than 0, then excitation is possible. If not, excitation costs an energy and it's not energetically favorable. So, and the minimum when V and P are anti-parallel, therefore what we have is like E of P, let me write it, minus Vp should be less than 0 for excitation. And now if there is no excitation, there is no dissipation, right? Because you have to absorb, give or take an energy, and if you cannot absorb, give or take energy, you just flow without dissipation, and that's the superfluid. And let me just unpack what this means. Then if superfluid or the fluid moves with the velocity, I just simplify this. V is bigger than E of P divided by P. So this is, if you want there, like, let me write cases. So this is case 1. Then so this condition is satisfied. Excitation happens, and this is viscous flow. Case 2, if V is less than this, E of P, then no excitation. That means no dissipation. That means superflow. Fluid should move without.
Like the molecule just tunnels over.
It is not like a single molecule. It's actually a little bit more complicated than that. And that's why I am like spending so much time on that. It is like full many-body system, right? It's the full many-body system decides what's going to happen, but we encode it in like an elementary excitation. We are thinking about the particle. I'm going to draw pictures of these particles in a little bit. But there is no more molecules anymore. There is now like a cloud of particles. They are like complex objects, and they determine what the system does. And superfluidity comes from that behavior. Now, so this is the result. And let me give you a couple of examples. So example 1. Let's consider simplest thing, ideal Bose gas. What is the energy dispersion in an ideal Bose gas? I think everybody knows that. P square over 2m. So this is P square over 2m. And let's draw spectrum. So this is E of P. This is P. And this is just quadratic. And this is E of P. And the condition says if E of P is, or if, like, what is, so this is E of P curve. What is the line for V times P? Or what is the curve for, right? V is a constant. P is the parameter here. It's just like a line, right? Something like this. This is V dot P. So this is E of P. And you can see V times P is bigger than epsilon. Like, right? This condition is satisfied no matter what. Because a parabola and a line is going to intersect like this. Their origin is fixed. No matter what, red line is going to be over blue line in some region of space. And this means this is case 1. Case 1. And what was case 1? Case 1 was excitation happens. That means there's going to be viscous flow. Then this is no superfluid. So that's why we say ideal Bose gas. It can have a Bose-Einstein condensate, but it is not a superfluid. The second example is helium. So example 2. Helium-4. And Landau, I think, based on experiments, predicted the spectrum of helium. But not today we know it from like both experiments and also quantum Monte Carlo. let me show you what it looks like. And it is also going to tell you how many-body physics can be quite different from what we classically expect. So this is, again, P. Initially, this is like linear, like this. So this is linear. And then at some point, it turns over. There's like a minimum, and it just goes up like this. Okay. And now I need to draw a line. So this is E of P, and so this is now a line, I don't know, something like that. This is P times V, and now you can see there is like a critical point like this, for example, here. If you draw a line, right, so this is going to define some critical velocity, and if the fluid motion is, if V is less than V critical, then this is case 2. And what was case 2? Case 2 was V is less than E of P over P, and there is no excitation, no dissipation, that means superflow. Case 2 and superflow. If V is bigger than or equal to Vc, then this is case 1. So this is case 2, this is case 1, and viscous flow. And this is called, I think, I'm not sure, but I think it could be called critical Landau velocity. And basically, until exactly like rotation, right? In the rotational case, you rotate the fluid, but the fluid doesn't rotate. But once you reach the enough angular velocity in which you can give a circulation h over m, you put like one vortex, and then fluid starts rotating. In this case, you push the fluid, and fluid doesn't dissipate. But if you keep pushing the fluid, at some point, it's going to dissipate. And there will be an energy, and then it's not going to be a superfluid anymore. For future reference, let me give you one more example, but this example you don't need to worry about for the moment. So this is example 3. Superconductor. So the dispersion for superconductor, we will see why this is like so. Let me just give you the result. So it's like parabolic, but there is like a gap. So there is like a gap. And if you draw like a line, right, there's still a critical velocity. And in the case of superconductor, we also can, because if velocities are less than V critical, there's also like a superfluidity. In some sense, we can also think about superconductor to obey or to satisfy the condition for superfluidity. And this one is going to be connected to so-called Meissner effect and all those things. But for the moment, just be prepared. There's more to come. Good. Any questions? Let me talk a little bit more about helium spectrum because it tells us a lot about many-body systems, and then I'll finish it there. So this spectrum, let me copy this. There are different things happening here. Maybe I can push it down. And let me erase this. I'm not interested in that anymore. So there are like different portions of spectrum. So this portion is like, if you want, small momenta, or if momentum is small, this is long wavelength. It's also long wavelength and low energy. If you want, this is the most effective region of the fluid. And these are like, you can see this is linear. And what other linear dispersion do we know in physics? Like any other? right? Dirac point, but like some simpler than Dirac. Like even in high school, we know about linear spectrum.
Air,
Huh?
air friction.
Air friction, like in anybody who took condensed matter 409, we start in 409 with phonons, right? Like there's like so-called phonons, and they also have like linear dispersion. But if you don't know phonons, no worries, it's exactly like photon, right? Photon is also E is equal to PC, right? The linear spectrum. And all of these things give rise to, like, for example, phonons. What is the picture? You have like a, so this is a cartoon, but let me just go over the argument anyways. So you have like a single particle moving with velocity v, and there are other particles around it. And because it moves, it also drags other particles with it. And because of this effect, it looks like a complex, like some cloud, right? For example, the mass looks a little bit bigger. There's like a mass enhancement, and it is not the point particle anymore, right? So this is, that's why it's like also like a density oscillation, and it's like a phonon. And if you look at, for example, specific heat of helium-3, you are going to find A times T to the cube. And this T cube is exactly like Debye law, and derivation is exactly the same. You use both occupations, and you use the integrals and all these things the same, and you find specific heat to be T cube. And the similar calculation for NS, like the superfluid density as a function of temperature, gives n minus A times T to the fourth. Okay? So this is the phonon part of the spectrum. There's also other parts. Any questions? So this piece is now this is like not small momentum, long momentum. This is like a high energy mode, and you can see there's like a minimum here. That's why this is sometimes called Roton minimum. And here the spectrum is not linear, but it is something like E of T is equal to some gap. So there's like some gap here, delta, plus P minus some P0 squared, and there's some curvature here, which is, I'll use Q mu there. And the cartoon for this, let me copy this thing, is a little bit different from that. So here, particle moves, and all the other particles are moving along like a density blob. Here, all the other particles are getting out of the way. If you want, this guy is going like this, guy is going like this guy is like going like this, and this guy is going like this. And so this is what we call Roton. And Feynman considered this to be kind of like a smoke ring. I think everybody likes smoke ring. You probably have seen a smoke ring, right? You just, I don't know, they devise some giant tool and they just throw it. If you look at the ring itself goes forward, but particles inside the ring, they just circle back. And like, okay, that's it. So basically, we are on like a phenomenological discussion, and we are just looking at the experiments and trying to understand. But the message is like complex, many body interactions. They basically erase individual particle identities. Now we cannot go and look at individual particles, and you cannot say like little helium atom or molecule. It doesn't have any sense anymore. Rather than that, we have like quasi-particles. So these are like clouds of complicated objects that the system gives rise. So this is like an emergent degree of freedom, but they are kind of like our particles. And these quasi-particles sometimes are called elementary excitations. And the way we understand now is also like from this Galilean invariance. So far we didn't do any many-body physics. Good. Any questions? Okay, next time I'll start superconductors. I'll also spend like maybe 1 week for phenomenology of superconductors. And then we are going to start a little bit more mathematics after that. Good. Thank you.